In this video, we're going to look at how to calculate formal charge. Formal charge helps us figure out which Lewis structures to use as we're going to find the most stable structure. So what we're looking for is to have an overall charge of 0. So that either means all of the atoms in our molecule are going to have a 0 charge, or we're going to have a plus charge on one side and a minus charge on the other side, canceling each other out or balancing each other to give us an overall 0 charge. So let's look at this H2O molecule. So to calculate formal charge, we're going to look at the valence electrons of an atom, and then we're going to subtract this number by the number of lone electrons that we have. So it's not lone pairs, it's each individual electron. And then further, we're going to subtract the number of bonds. So if we have a double bond, we would subtract 2 because there's 2 bonds attached to that atom. Sometimes you may also see this as being 1/2 the bonded electrons. And that's simply saying that since there's 2 electrons to a bond, you would only do half of it, meaning you would only have 1. And that's the same as just the number of bonds. So we're going to go with this first definition. So if we take this equation into account, if we look at the oxygen, the central atom of this molecule, oxygen has 6 valence electrons. And then we have 1, 2, 3, 4 lone electrons. Not lone pairs. We have 2 lone pairs, but remember, we're trying to find the lone electrons. So we have 4 lone electrons, and how many bonds does it have? 1, 2. It has 2 bonds. So when we subtract our lone electrons and our bonds from our total valent electrons, we get a charge of 0. This is extremely stable. Now, hydrogen is a little different as it doesn't follow the octet rule, and it only needs 2 valence electrons in order for it to be stable. So you can see that there's 1 bond, there's 2 electrons that make it up, it's going to be stable. But if we wanted to do this equation on hydrogen, we can do that as well. Hydrogen has 1 valence electron. And how many lone pairs does it have? 0. How many bonds is it attached to? This one's attached to 1, this one's attached to 1. We would calculate them separately. So each hydrogen is attached to 1 bond, so we would subtract 1 bond, giving us a charge of 0. Let's look at a charged atom. So again, we know the hydrogens are all going to have a charge of 0 because they only have 1 valence electron and they only have 1 bond. So we don't have to worry about those, but we have our central nitrogen here with a plus charge. This is a cation. So here, we're going to take our nitrogen's valence electrons, which it has 5 of, and we're going to subtract the number of lone pairs. We can see there's 0 lone electrons, so we're subtracting 0. And then we're going to subtract the number of bonds. It makes 4 bonds with hydrogen, so we're going to subtract the 4, giving us plus 1, a positive 1. That's its formal charge, and it's reflected in its charge here. Now, I want you to try this one on your own. Try to find the formal charge of the hydrogen. While you do that, I'm going to write another one on the right. Okay, let's look at our hydroxide, our OH. So again, we don't have to worry about the hydrogen because we know it's already going to have a charge of 0. So let's look at the oxygen. Our oxygen has 6 valence electrons. We're going to subtract the 6 lone electrons, and then we're going to subtract the 1 bond. That gives us a charge of -1, and that's indicated by a negative charge here on the oxygen. So when we have a negative charge or a positive charge, and it's not 0 or there's not the opposite charge to cancel it out somewhere, we want to look and see if our structure has resonance anywhere. We want to see if we can move this charge to a different atom or if we can eliminate it altogether. because there might be a more stable structure that we just haven't written yet. So if you get a charge that's not 0, you're going to want to look for resonance. Now here, the only thing we could have done is move a lone pair to form a double bond, but hydrogen can't form a double bond, so this is the only structure that we can write. Now let's look at nitrate here on the right. Now we have a nitrogen bonded to 3 oxygen atoms. We don't have hydrogen anymore. So we're going to have to look at every single atom and determine what its charge is. So let's start with the oxygens on the outside. I'm going to start with this left oxygen. We have 6 valence electrons minus 4 lone electrons minus 2 bonds. That gives us a charge of 0. Now if we look at the bottom one, again, 6 valence electrons minus 6 lone electrons this time, minus 1 bond, gives us a -1 charge. Now let's look at the one on the right. 6 valence electrons minus 6 lone electrons minus 1 bond gives us a -1 charge, just like the bottom one. Now let's look at nitrogen. So for nitrogen, we have 5 valence electrons. And we have no lone electrons, but we have 4 bonds. So we're going to subtract 4, giving us a charge of +1. So now we have a lot of different charges. We have 0, we have 2 negative charges, and we have a positive charge. So what do we do here? Well, we want to find out what the total charge is. So we're basically going to add all these charges together. That's going to be our total charge. So -1 plus -1 plus 1 gives us overall charge of -1. So this structure, we would put a negative charge on it. But where is that negative charge going to be? We found a negative charge on this right oxygen and also on this bottom oxygen. So where do we put it? Well, this is where the resonance comes into play. If I delete this left side, I could have also drawn this structure where the double bond is on the right oxygen rather than the left. And that would make this left oxygen also have a charge of -1. Or I could have written it with the double bond on the bottom oxygen, giving the left and the right oxygens the negative charge. So where does this negative charge actually go? Well, this negative charge is going to be distributed everywhere. So all 3 structures that I made, the 2 blue and the 1 white, they're all valid structures because we're going to have the same overall charge everywhere. Nitrate is a negatively charged ion. So there is a -1 charge. We just don't know where it is. It turns out it's in all 3 of our oxygens at the exact same time. That double bond goes to all 3 oxygens at the same time. This is the resonance structure. So that negative charge is being distributed everywhere. So any one of these structures is valid because it minimizes our charge. So let's look at this sulfate ion. Now, it's a similar situation to the nitrate ion in that we have a central atom bonded to a certain amount of oxygen. We don't have any hydrogens present. So we're going to have to find the formal charge of all 5 of these atoms and find what the minimum charge would be. So, if we start with our oxygen, just like we've been doing, if we start with this top one, we're going to have a 6 valence electrons minus 6 lone electrons minus 1 bond, giving us a -1 charge. Now this one on the right is the exact same thing, so we can give that a -1 charge too. Now the left and the bottom one both have a double bond, so let's calculate this one. We're going to do 6 minus 4 lone electrons minus 2 bonds, giving us a total of 0. So this is a neutral charge. That means that this one on the left is also a neutral charge. So right now we're at a -2 charge. We want to see if we can get that closer to 0 or if we can make some other structure that'll make it closer to 0. So let's look at the sulfur now. Sulfur has 6 valence electrons and it's bonded to 2, 4, 5, 6. It's bonded to 6, or it has 6 bonds. It's bonded to 4 atoms, but 2 of them are double bonds. There's 6 bonds total, no lone pairs. So we can subtract 6, giving us an overall charge of 0. So that means that this molecule has an overall charge of -2, because we have two -1 charges. But again, that same question comes up. How do we know that the charges go to the top oxygen and to the right oxygen? Well, that's not necessarily true, because we could have drawn the double bond on the top and the right. Or we could have drawn the double bond on any of the two oxygens, and the other two would have that negative charge. So this sulfate ion has multiple resonance structures. So that negative charge is distributed across all of those oxygens. The one that we drew just has it on the top and the right.